I've got the answers to the two problems that I left you with at the end of the last video up here. So our formula for h of k of x is 1 over root x, and our formula for g of k of x is the square root of x plus 2. What I want to do now is I want to start talking about the domain of our functions. And let's do that with this example here, the 1 over the square root of x. So I built that using h and k. Now, if we think about it, this was our assembly line. We were going to plug into k, and then we were going to plug into h. Okay. And k told me to take the square root of my input, and then h told me to take the reciprocal of whatever my input was. Now, in order for me to be able to do this, I have to be able to do both things. Okay? So, if I think about the domain of k, the domain of k would be that in order to take the square root, I need x to be bigger than or equal to 0. Okay? And in working this out, I think it's going to be simplest to just write the inequality that describes the restriction that I have on my x values. I'm ultimately going to give my answer in interval notation, but in the figuring it out stage, I think it's going to be easiest to have it written as an inequality. Okay. All right, and so then that's going to spit out the square root of x. If I take an x value and I plug it in, that's what that's going to spit out. Now, if I look at what h is, h was the reciprocal function, so the domain there was that x can't equal 0. But what I need to remember is that with all functions, x is just a placeholder for whatever my input was. And my input to h is the square root of x. So this restriction becomes the square root of x cannot equal 0. Now, it turns out that the square root of x will only equal 0 if x is equal to 0, because I can square both sides and get, okay, x is not equal to 0, and I can check that very quickly that that actually works. Although you do want to remember, if you solve an equation or a non-equation by squaring both sides, you always do need to check. Okay. All right, so what that means is that my domain for this function composition, h of k of x, is just everything that's bigger than or equal to 0 that isn't 0. So it would be strictly positive numbers. Now, in this particular case, I can pretty much see that that's the domain by looking at the result here. I can see, because I've got the square root of x in the denominator, I can see that x can't be 0. And because I've got to take the square root of x, I can see that it has to be bigger than or equal to 0. So I can sort of see both things that I'm doing there. You do want to be careful, because sometimes you're going to, in the process of simplifying your formula, you're going to lose track of the way you built things. Let me just give you an example of that. Let's suppose that f of x was the square root of x, and g of x was x squared. Now, if I take a look at g of f of x, okay, so that means I'm plugging f of x into the g function. So I'm taking g of f of x was the square root of x. So that's taking the square root of x and squaring it. Well, if I square the square root of x, I'm going to just get x. If I just look at that result, I'm going to think the domain is all real numbers. But it's not, because I got here by first taking the square root and then squaring it. So if I take a look, the domain for G, the domain for F, because that was the first thing that I did, was that X had to be bigger than or equal to 0. Now, the domain for G, that was the squaring function, so that was just all real numbers. So for that didn't add any restrictions to it. If it did, I'd have to make sure that not X, but the square root of X satisfied those restrictions. In this case, though, I've got to say that my domain is X bigger than or equal to 0. So it would be everything from 0 to infinity. If, in the process of simplifying a function composition, you lose information about the restrictions you had on X, it is necessary to write them as part of your formula. Because if I just write X, I'm going to think that that comes with its natural domain, which is all real numbers. But this function, g of f of x, is not the function x with a domain of all real numbers. It's the function x with a restricted domain of non-negative numbers. So do be aware that if in the process of simplifying things, you lose some information about the restrictions on x, it's necessary to record those. Okay. All right, let's just try one more of these. Let's let f of x equal x plus 2 and g of x equal 1 over x. And let's take a look at g of f of x. Let's find a formula for it, and let's find its domain. I'm going to actually find the domain first. Okay. So the first thing that I'm doing is f. I'm plugging into f, and so that says that domain is all real numbers. There are no restrictions on that because I can plug in anything to that function. I can add 2 to anything. For g of x, the restriction is that x can't equal 0. But what I'm going to be plugging into g isn't x. What I'm going to be plugging into g is f of x. So that restriction becomes f of x can't equal 0. Or x plus 2 can't equal 0, which means x can't equal negative 2. So no restrictions from the first step, but in order to be able to take the reciprocal in the second step, x can't equal negative 2. Now I know that means my domain is going to be a union of 2 intervals, from negative infinity to negative 2, union negative 2 to infinity. Now, if I take a look at g of f of x, that would be g of x plus 2. Now, the g function just tells me to take the reciprocal of my input, and so that would just be the reciprocal of x plus 2. Now, this is a case where it is, I think, simpler to see from that result that x can't be negative 2. But there are times when in the process of simplifying what you get, you lose some information. So it's always good when you're looking at the domain. I'm fine if you come up with a formula for the function and then look at the domain, as long as you look back over your process and make sure that you didn't do any simplifications that have you losing information about restrictions on x. So in general, let's just write this down. The domain of f of g of x is all x values in the domain of g, okay, because I've got to be able to do that first step, such that g of x, which is of course what I'm going to be plugging into f, is in the domain of f. So it's basically a two-step process, and you need to make sure that you're looking at both parts as you calculate what that domain is.